Welcome students. Today I wish to discuss shortest path problem. I tell one of the example for single source shortest path problem called Dijkstra algorithm. First of all, I tell about what is single source shortest path problem. Consider you are having a directed or undirected weighted graph with n vertices and m edges, and the weights of all edges are non-negative. You are also given a starting vertex S. This problem aims at finding the length of the shortest path from a starting vertex S to all other vertices and output the shortest path themselves. This problem is called single source shortest path problem. From single source S, what is the shortest path for reaching every vertices in a graph? This is called single source shortest path problem. So one of the example for single source shortest path problem is Dijkstra algorithm. Okay, I read the general algorithm for Dijkstra. It maintains a list of unvisited vertices in an array. Okay, just setting the flag, all flag values to false. And it chooses a vertex, that is source vertex, and assigns a maximum possible cost. There is infinity. All the other vertices set to infinity to every other vertex. Next, the cost of the source remains 0 as it actually takes nothing to reach from the source to vertex itself. Initially, the cost of the vertex is source vertex is 0. In every subsequent step of the algorithm, it tries to minimize the cost for each vertex. Initially, it is set as positive infinity. Okay, in every subsequent steps, the algorithm tries to minimize the cost for every vertex. Here, the cost can be a distance, money, or time taken to reach the vertex from the source vertex. The minimization of cost is a multi-step process. For each unvisited neighbor, for example, you have started from vertex 1. Consider we have a neighbor 2, 3, 4 of the current vertex 1. Calculate the new cost from the vertex 1. For example, the new cost of vertex 2 is calculated as the minimum of the 2, that is existing cost of the vertex 2 and the sum of the cost of vertex 1 plus cost of the edge from vertex 1 to 2. Okay, for example, already you have started from one vertex, okay, V1, and already you have some weight to reach V2. Okay, now you identified the connection between V1 and V2. Just to compare further, at the time, just to compare existing cost of vertex 2 and the sum of the cost of vertex 1 plus the cost of edge from vertex 1 to vertex 2 and identify the minimum amount, okay, and update it. When all the neighbors of the current node are considered, it marks the current node as the visited node and it's removed from the unvisited list. Okay. Next step is select a vertex from the list of unvisited nodes which has the smallest cost and repeat the step of previous step, that is updating the weight. Repeat again, select a vertex from the list of unvisited nodes which has the smallest cost and repeat step 4. At the end, there will be no possibilities to improve it further and then algorithm ends. All the vertices are visited, process remains, algorithm ends. This follows greedy strategy. What is greedy algorithm? A greedy algorithm is any algorithm that follows the problem solving heuristic of making the locally optimal size at each stage. Okay, stage by stage, it tries to identify the locally optimal solution with the intent of finding the global optimum. Okay, this algorithm follows a greedy strategy. For example, you have a graph, I just apply a Dijkstra algorithm for this. Okay, consider starting with as okay, each there is totally 6 nodes in the graph. Each edge carries weights. Okay, consider the starting with as okay, I just consider the starting with as mark as visitor. The cost from source to source there is one is 0, and I have 3 edges which is connected with there is nodes which are connected with 1 or 2, 3 and 4. Okay, I wish to explore these 3. Okay, mark initially mark 1 as visitor of visitor. Next, assign a cost 0 to vertex 1, and the remaining state, all the vertex except source will set as infinity because we don't know the cost, because we didn't explore the other vertices in the graph. So the distance will be marked as infinity for all other vertex initial state. Source vertex cost set as 0. Okay. According to the greedy strategy, I need for traversing all the nodes from the source to all the nodes, I need to identify the local optimal size. Here, based on the distance, the local optimal size is next node to be visited is see here 1 to 2 cost to 3, 1 to 3 cost to 4, 1 to 4 cost to 2. So 2 is has less cost. Okay. That is corresponding to the vertex 1 and 4. This is visited. Now, for each of the unvisited neighbors, okay, for each unvisited neighbor that is connected with the source are 2, 3, 4. As I told already, 3, 2, 3, 4. Okay, calculate the minimum cost. That is minimum cost of the vertex under consideration, comma sum of the cost of vertex 1 and connecting edge. Okay, mark 1 as visitor. Okay, in the diagram, the border plot. The new state will be looking like this. Initially, before exploring, it has infinity only. Now we have marked number 1 as visitor. So the edges which is connected are updated. So for 1 to 2 already we have a there is cost as infinity. Now it is compared with the 3. 3 has less value when compared to infinity. So we have changes. Similarly, here infinity be replaced with 4. Here also the infinity replaced with 2. Okay. Next, choose the unvisited vertex with minimum cost. That is vertex 4. So we have updated cost now. Here 3, here 4, here 2. So which one costs less when compared to other vertices? That we have explored 2, 3, 4. We have explored. From this, the less cost is 2. So that is corresponds to vertex 4. So choose the unvisited vertex with minimum cost, that is vertex 4, and consider all its unvisited neighbors, that is vertex 5 and vertex 6, and calculate the minimum cost for both of them. Initially, it was infinity. We have selected 4 no, and we have marked as visitor, and we need to identify what are the vertices which is connected with the one that is 4, which is 5 and 6. Initially, the cost will be infinity. Now, the cost will be 2 plus 1, 3. Okay, this will be compared against the infinity value. So 3 is less than infinity, no? So it is updated here. Here also, from source to destination via 4, the cost of reaching destination 6 is 2 plus 4 6. Already it was infinity, now it is compared with infinity, so 6 is less, so I have updated as 6. Okay, so the resultant graph looking like this. You have updated all the costs. No node has infinity, no node has infinity. Next step is choose the unvisited vertex. Okay, you have visited one and visited four previously. Now choose the unvisited vertex with minimum cost. Which one is minimum cost? For example, according to this, after exploring 1 and 4, according to this cost, from source to destination, the minimum cost is 3 only. That is this value only, which is connected with node 2. So next 2 will be explored. Okay. So choose the unvisited vertex with minimum cost, that is vertex 2 or vertex 5. Vertex 5 also has cost 3. 2 plus 1, 3. But according to the order, you can take this one. Okay. It is arbitrary. You can take anyone because it both edges, the path has same weight cost, no? So consider all its unvisited neighbors. Okay, and calculate the minimum cost for both of them. Okay, so cost for this one is already calculated for that is for reaching, that is for reaching 5. Already we have 3. Okay, which is less cost only. If you use path 2 means, okay, we use path 1 to 2, then 2 to 5 means the cost is 5. So already we have 3, now 5. So since 5 is greater than 3, we don't no need to update the weight values. Okay, in a similar way, cost for reaching 3, via 2 okay, has 7. Okay, already we have direct connection, no, which cost only 4. Okay, no need to update this. Okay, in a similar way we can process the edges which is associated with node 2. Okay. Next, choose the unvisited vertex. Next vertex to be visited is from the source to the destination. On the unvisited nodes, we need to select which one cost less. Okay, so other nodes are 3, 5, 6. So when I take 3, 5, 6, 5 has less cost because 3 plus 2, 5. Okay, next. Next one is 6. 6 has high cost. 2 plus 4, 6. Okay. Via 2, 3 plus 4, 7. So don't take 3. Okay, via 2, 3 and 4, when you add 3 and 4, cost 7. But via 2, if you reach 5 means the cost is 5. So select 1 to 5. Okay, choose the unvisited vertex with minimum cost. Consider vertex 5. And consider all its unvisited neighbors. For example, 3 and vertex 6. Calculate the minimum cost for both of them. Now, the current cost of the vertex 3 is 4. Okay, and the sum of the cost of vertex 5, that is 3 plus 2, 5. The cost of edge 5 to 3 is 6. So already we have high cost now, so no need to select this one. Already we have 4, which is less when compared to this cost. Okay, then the cost of vertex 3 won't change. Now the current cost of the vertex is 6. The 6 is 6. Okay, and the sum of the cost of vertex 5 plus cost of edge 5 and 6, 3 plus 2 is 5. Okay, so hence the cost of vertex 6 changes to 5. Okay, so when I explore 5, so the cost of reaching the 6 is already 5. Okay, already 6, actually already 6. Now it is changed to 5. Why means via 1, 2, 1, 4, 5, and 6. It cost 5 no, so this weight has been updated. Okay, hence the cost of vertex is changes to 5. Next, choose the unvisited vertex with minimum cost, that is vertex 3, and consider all its neighbor. Okay, unvisited neighbors. No unvisited neighbor that corresponds to 3 until now. So just do nothing. Okay, so mark it visited. Let's look at it. Final vertex to be visited is 6. Choose the vertex, unvisited vertex with minimum cost, that is vertex 6, and consider all its unvisited neighbors. Okay, already the weight is updated. It has minimum cost only, so no need to worry about this. Okay, so this is the final step. Okay, what we interpret from this? From source to every other distance, we have recorded the shortest path. From source to, there is 1 to 2, the shortest path is 3. 1 to 4, the shortest path is 4. 1 to 3, the shortest path is 4. 1 to 4, the shortest path is 2. 1 to 6, the shortest path is 5. Through this path. This path also recorded. For 1 to 5, the shortest path is 3. Through this path. Okay. So this is a single source shortest path problem. So I show the implementation. Okay, include the header file and set the maximum size of a. There is a dimension of a graph is 10 by 10. It is number of graphs. The number of vertices in the graph is 10. And set the infinite value as maximum value. Okay. Because initially we set the distance matrix as infinity. Okay. So here I have used adjacent matrix for simplicity. Okay. To create a 2-dimensional array which records the what are the nodes connected with by using edges. Okay. The association between the vertices are using adjacent matrix. For looking purpose, you use I and j, and n for number of vertices, u for sorting vertex. Just to get this number of vertices by using count statement, and we use loop two loops for getting the adjacent matrix. There is a connection, it is set as 1, otherwise it is set as 0. Now enter the starting node. Starting node is u. Just call the Dijkstra algorithm to pass in the graph and there is a number of vertices and sorting vertex. In Dijkstra algorithm, we are passing the adjacent matrix, number of vertices, sorting. There you are maintaining a cost matrix. Okay, there is a data which is retrieved from graph matrix and distance matrix, the distance array and predecessor array. Okay, which path it came from, that information is stored in this array. And the visited array, this is initially set as false. Then count the number of vertices visited. Minimum distance is used to record the minimum distance between the node. And the next to be visited is recorded ing for looping. Here we use two loops to set the infinity value if there is no connection between the nodes. Okay, if there is no connection, for example, from vertex 1 to 5, if there is no direct connection between means, just set as infinity. If there is a connection, insert just set the matrix value to the cost matrix. It is simple. Next, by using for loop, just update the distance matrix. Okay. Just use cost of starting node of I can update it, and predecessor node is a starting node. Okay, and visited of I equal to 0. Okay, for all this is for initialization purpose. We are making all the visited. There is unvisited by using 0, and visited value all the values set as starting node. Okay, distance value set as cost. Okay, so cost of starting node to I, it has infinity value only. You because if there is no connection means we have infinite only. So that is set actually. Next, starting node of distance set as 0 and making the starting node of visit, there is visitor of starting node as 1 and number of node visited until now is 1. Next, in while loop, until number of edges reaches, we have to compute, that is find the shortest path. Initially set mean distance value as infinity, that is maximum value, and we are using the loop to find the adjacent nodes. Okay, first we are having some distance value, that is infinity value initially, and distance value is compared with the minimum distance. Okay, if it is less means, and also it didn't visit the particular node, that is a neighbor node means, just record minimum distance equal distance and the next node equal to I. Next node means adjacent node. Okay, distance of I is less than minimum distance, and also it is not visited means just record the minimum distance and record the next node to be visited. And the next node, if it is less means next node is set as visited or next node is set as 1, and by using for loop checking the adjacent node. If minimum distance plus cost of the adjacent node, okay, is less than the distance, current distance means just update it. That is distance of I equal to minimum distance plus cost of next node of I. Okay, and also you can have to record the predecessor. Okay, so here we are making the update. Already you have some weight, maximum weight value for a distance, particular node, the distance of I. So now it is compared with the minimum distance, neighbor node distance, current cost with the neighbor node distance. If it is less means we just update it, otherwise do nothing, and increment number of node visited as step by 1. Already count 1 node. If you are visiting another node, then the count will increment by 1. In a similar way, the loop executes. If this loop will terminate when count reaches n. Okay. Finally, we are printing the path. Okay, from source to destination. Which one is the path? That path along with the distance also printed. Okay, just use a loop. If I is not a starting node, so if you are not checking this condition means it form a loop actually. If I is not a starting node means just print the distance and the path. Path stored in variable predecessor. Okay, from the destination to source. Okay, what is the path that is available in the predecessor? Okay. Just iterate the loop until j not equal to start. From source to destination, we can identify the path. For all the nodes, this process is done. Okay, that is why we have used it. Okay. So in this way we can implement this is the algorithm. It is simplest way. If you use adjacent matrices, simplest way. Running time will be order of n square. Okay, we can also use adjacent list to reduce the running time. Okay, further we can use C++ STL min-give concept to reduce the running time to log linear, that is n log. Okay, we meet in the next class.